Yeah, so our next speaker is Masahiro Watari with the talk titled Motivic Hilbert zeta functions on curve singularities and related invariants.
Okay, thank you for the introduction. Okay, so today I talk about Motivic Hilbert zeta function. And so my talk is divided into 3 sections. So first, we'll start with this question. So how can we describe the geometry and topology of curve singularity in a unified way? So to answer this question is the purpose of this talk. Okay, first, let's fix annotations. So in my talk, she is always reduced curve. Maybe it's not irreducible over complex number field, and P is its singular point. So in my talk, we always call the pair C and P a curve singularity. And this notation CPL assigns punctual Hilbert scheme of degree L. So that is, this is the set of length L subschemes of C, which is supported at P. And this notation is always the Grothendieck ring over C varieties. And the notation, the bracket X, is the class of a C variety X in the Grothendieck ring. And in this setting, we can define for the given curve singularity, the Motivic Hilbert zeta function is defined in this way. So, roughly speaking, Motivic Hilbert zeta function is a formal power series ring whose coefficients are class of punctual Hilbert scheme in the Grothendieck ring. This is our main object today. And let L be the class of the affine line A1 in the Grothendieck ring. So the following fact is known. If punctual Hilbert schemes admits an affine cell decomposition, its class in the Grothendieck ring is a polynomial in this large L. So in such a case, we always notation, this notation for Motivic Hilbert zeta function. So we add L as a variable. So in this situation, our first main theorem is stated as follows. If each punctual Hilbert scheme admits an affine cell decomposition, then the Motivic Hilbert zeta function gives the generating function of Euler numbers of punctual Hilbert schemes. So in this talk, Chi assigns the Euler numbers. This is our main theorem. And so next we consider a bit special situation. So plane curve singularity with a single fuse pair. For this singularity, the following fact is known. So if curve singularity is a planar singularity with a single fuse pair, then each punctual Hilbert scheme admits an affine cell decomposition. So we can say it follows from theorem 1. So for this singularity, a plane curve singularity with a single fuse pair, theorem 1 holds. And next, let's consider some concrete examples. So especially we consider AD singularities. So first, consider A1 singularity, an ordinary node. So for this singularity is not irreducible, but it is known that any punctual Hilbert scheme for this singularity admits affine cell decomposition. So the Motivic Hilbert function is this, and it follows from theorem 1, the generating function of Euler numbers given in this way. So substitute 1 to L and replace T with Q. Then we obtain this generating function of Euler numbers. And in a similar way, for A to D singularity, the Motivic Hilbert zeta function becomes this, and by theorem 1, we obtain the genetic function of Euler numbers in this way. So next, we consider E-type singularity, E6 and E8. So similar to the previous slides, we can obtain the Motivic Hilbert zeta functions, and by theorem 1, the genetic function of Euler numbers in these ways. So originally, the Motivic Hilbert zeta functions are defined as a formal power series in T, but in these concrete examples, these became a rational function in T. So in general, the following fact is known. So if Cp is a reduced curve singularity, then its Motivic Hilbert function is a rational function in T, and its denominator is given by 1 minus T to the power S. And this S is the number of the branches at T. This fact is known. Okay, so next we consider the relation between semigroup and the Motivic Hilbert zeta function. So here, gamma is the set of all orders of F in the local ring of C at T. OCP is the local ring of C at T, and this set is called the semigroup of the local ring OCP. And a subset of gamma is called a gamma semimodule if it satisfies delta plus gamma contained in delta. So when this relation holds, we call this delta a gamma semimodule. And this notation is the set of all gamma semimodules. So definition, for a gamma semimodule delta, we define its codimension the number of the element of gamma which are not in delta. So then the generating function of gamma semimodule is defined to be this equation. This is called the generating function of gamma semimodules. So for this generating function, we can prove this relation. So this is our second theorem today. So if the singularity is a plane curve singularity with a single fused pair, then Motivic Hilbert z function is generating function of delta semimodules. And by theorem 1, so this equals the generating function of Euler numbers of punctual Hilbert schemes. So this is our second theorem. And next, so let's briefly recall some known result about Euler numbers and other invariants. 2016, Maulik proved the following relation. So for a reduced curve singularity, the genetic function of Euler numbers of punctual Hilbert schemes equal to the right-hand side expression. Here, LCP is the link associated with the singularity, and PLCP is the home-fly polynomial. So it is known this relation between the genetic function of Euler numbers and the home-fly polynomial. So this is proved in 2016. And also, regarding genetic function of Euler numbers, so it is expressed in this way. So this is the relation between Euler numbers and deformation theory, where in the right-hand side, VHs, so these are several strata of universal deformation of given singularity. And delta is the delta invariant of singularity. So genetic function of Euler numbers of punctual Hilbert scheme is related to the deformation theory. So by using these known results, we can conclude. So if a plane curve singularity has a single piece pair, in this case, its Motivic Hilbert zeta function is related to these known invariants. So this is our third main theorem today. Okay, next we come to an application of Motivic Hilbert zeta function. So here is a theorem. So Pandey and Thomas prove the following theorem. C is an integral locally planar complex algebraic curve. Then there exist integers which satisfies following relation. Again, left-hand side is the genetic function of Euler numbers of punctual Hilbert scheme. And in left-hand side, so left-hand side is expressed in terms of q to the 1/2 minus q to negative 1/2. So they proved this relation in the context of curve counting on Calabi-Yau threefold. So actually, the following is very well known, I think. So a bit classical, but so MacDonald proved this theorem in 1962. So now C is non-singular curve. So then we have this relation. Here, left-hand side is Euler number, but CL is not punctual Hilbert scheme, but the symmetric product of C. But in the case C is non-singular, symmetric product of C is same thing, the punctual Hilbert scheme C. Okay, this is very well-known classical result. And after this theorem, Kawai generalized this result in the following way. So Kawai allows the curve has some singularities. So now she has a curve with its singularity, the A1 singularity and S singularity. Then the left-hand side, the genetic function of Euler numbers of punctual Hilbert scheme given by this right-hand side. So here, M and N are number of singularities. So roughly speaking, if she has a singularity, then in left-hand side, we should add some information about singularity. And finally, we can generalize this result in the following way. So here, curve C has A1, A to I moves from 1 to D, and E6, E8. So she has these 4 types of singularity. Then the generating function of Euler numbers of punctual Hilbert scheme is expressed as in the right-hand side. Here, M0, Mi, and MD1 plus 1, MD2 plus 2 is the number in each singularities. And here, H1 and H2 are polynomials. So H1 is this, and H2 is given by this. And in this equation, we replace T by Q to the 1 half minus Q to negative 1 half squared plus 2. So then we obtain this generalization. Okay, this is our fourth theorem today. Okay, that's a bit earlier, so that's all my talk. Thank you for attention.
Thank you very much. Very informative talk.